Welcome back to the deep dive. You gave us a stack of materials that, honestly, they look like internal system security audits, maybe some developer notes,
Mm.
and they all focused on one critical question. How does something as mundane as a system configuration setting become the primary entry point for a root-level system compromise?
And that's really our mission today. We are going to dissect the security risks tied to environment variables,
Hmm.
especially when they interact with highly privileged programs.
Okay.
These variables are necessary, right? They
Mhm.
tell a system what resources to use, but their convenience, their accessibility, that makes them a critical security checkpoint.
So we're really looking at blueprints for escalation here. We're going from a basic concept to these layered attack vectors,
Hmm.
path manipulation, dynamic linking exploits, and something called capability leaking.
Right. And if you want to be well-informed on core system security, you have to understand this whole ecosystem. We need to look at exactly why environment variables, even though they have known inherent vulnerability in themselves, introduce these severe risks.
It's all about misuse and poor design.
It is.
Okay, let's unpack this and start with those foundational pitfalls, the things that aren't formal exploits, but just, well, bad choices that create the risk.
The first major issue is exposure, plain text storage. Environment variables are almost always stored in plain text, and they're often accessible by any process that can, say, view the process list or its memory space.
So you're talking about things like API keys, database credentials.
Exactly. All those sensitive secrets. If you're relying on environment variables to hold them and you don't have really rigorous memory protection in place, that data is just exposed.
That makes sense. It's a common shortcut, especially in dev environments, but a huge risk in production. And related to that is just how dynamic they are.
Correct. They are dynamic, they're changeable at runtime, and this introduces the risk of, well, accidental or malicious overwriting.
So another process could just change a value.
A benign process with a memory leak, a malicious script, either one could alter a critical variable. So if your program relies on, say, VRX being a specific directory, and something else updates VRX to point somewhere malicious, your application's behavior is immediately compromised.
And if you scale that up into a big enterprise system, over-reliance on these things must create some serious configuration management headache.
It's a huge dependency risk. It makes version control really challenging, leads to inconsistencies, especially when developers make this one very common mistake, the hard coding pitfall.
They just assume the value will never change.
They assume that because they set it once in their shell, it's static, but it isn't. And the limited access control means it is inherently difficult to prevent unauthorized changes on a global scale.
So we've established the vulnerability, configuration is dynamic and exposed. Now we pivot from these poor design practices to how attackers weaponize core OS features that implicitly rely on these settings.
Right, and here's where the sources get really interesting.
Let's start with the linker, or the loader.
Okay, so the linker is a fundamental piece of the operating system. When your application needs to call a function that isn't built into its own code.
Like writing to the screen or encrypting some data.
Exactly. The linker finds that external library function. And this is often completely outside of a developer's direct control.
And the sources detail two main ways to do this: static and dynamic.
Static linking is simple but bulky. It just pulls all the library code it needs and bundles it into one giant self-contained file.
The upside is portability, I guess.
Portability is the advantage, yeah. The disadvantage is that if the library has a security flaw, your entire program is shipped with that flaw, and the file size is huge.
But dynamic linking is the default, and that's where the real opportunity for exploitation comes in.
Absolutely. Dynamic linking finds and attaches shared objects, those .so files on Linux or DLLs on Windows, during execution. It's efficient, saves memory, allows for easier updates, but
because the system has to decide where to find that code at runtime,
it relies on, you guessed it, environment variables.
and we're talking about variables like LDP reload and LD library path.
If a malicious user can set those, they can essentially hijack the whole linkage process. An attacker can set LDP or eload to point to their own malicious library.
So when the legitimate program launches,
It might be forced to load the attacker's code before the real system libraries. This lets the attacker intercept function calls, modify them, or just execute their own arbitrary code.
that sounds absolutely catastrophic, especially for privileged programs. But our source material had a pretty critical caveat here, didn't it?
It did, and this is crucial to note. Modern operating systems have mitigations for this specific attack, especially against SetUID programs.
How so?
Well, a SetUID program will often sanitize its environment. It might specifically ignore or just clear variables like LDP or reload to prevent this kind of injection when it's running with high privileges.
So that forces attackers to find simpler, maybe older methods.
It does. And while that linker attack has some mitigations, our sources point to an older, much simpler vulnerability that still works consistently: path manipulation.
The path environment variable vulnerability. This one is frighteningly simple.
It is. The path variable just defines which directories the shell searches when you run a command. The attack happens when a developer uses a system API call to run some external program, but they don't specify its full path.
Let's use the sources example. We have a C++ demo, today.cpp. It runs the system command date. The developer just assumes the system will find the legitimate usurban date.
Exactly. But if an attacker can create their own little executable or script and name it date,
A malicious one.
a malicious one, yeah, and then they update their path environment variable so their malicious directory is listed first.
Then the legitimate program, when it tries to call date, follows the path, finds the attacker's version first, and boom, it runs it.
And this is where it gets critical. If that original program, today.cpp, was running as a SetUID program owned by root,
Then the attacker's code, even if it's a simple shell script, executes with full root privileges. Okay, let's spend a moment defining SetUID because it really is the threat multiplier here. What does it mean for a program to be SetUID?
it means the program can run with the privileges of its owner, not the person who executed it. So when a root-owned SetUID program is run by a standard user, its effective user ID, the EUID, becomes root, granting it temporary high privilege.
That's necessary for things like the password program, right? It needs root to write to system files.
Precisely.
So when a path manipulation attack successfully hijacks one of these root-owned SetUID programs, what does that mean for the system's security?
It's game over. The attacker gains root privileges for as long as that program runs, and that compromises the entire system. And we connect this back to the CIA tried confidentiality, integrity, and availability. A root exploit hits all three.
Confidentiality is gone because they can read any file. Integrity is gone because they can alter any file.
And availability is gone because they can just shut down or destroy services. It's total control.
The underlying vulnerability here often comes down to one infamous system call, as detailed in our sources. The system call.
That's where the unsanitized environment variables often sneak in. The system command function is basically a wrapper for bin sheet command.
It just launches a shell.
It launches a shell, and by doing so, it automatically passes the entire environment of the calling process to that new shell, including a potentially compromised path.
And if the calling process is SetUID and running as root, the shell inherits those privileges.
Exactly.
Okay, so if modern Linux systems know about this danger, are there built-in defenses?
There are, and this is an important detail in the materials. Modern distros like Ubuntu 20.04 and Kali 2023 often use a shell called bin-dash as the default for binsh. And dash has a critical countermeasure.
What's that?
If it detects it's being run inside a SetUID process, it immediately drops its effective privileges. It changes its EUID back to the real user's ID. It's a fantastic layer of defense.
But the sources also highlight the cat and mouse game here. Attackers don't just give up.
Never. That specific mitigation relies on the system actually running dash. So an attacker can circumvent it by just updating the binsh soft link to point to a shell without that countermeasure, like binsh.
And they maintain their privilege escalation. It just proves that relying on one default defense is never enough.
It's never enough.
We've covered direct execution attacks, but the sources dive into more subtle, advanced vectors. Let's talk about capability leaking. This sounds like something out of a spy movie.
It is that subtle. Capability leaking happens when a privileged program tries to downgrade its own privileges, which is good security practice, but it fails to clean up properly first.
So it's like leaving the front door unlocked while you change from your root uniform into your user uniform. The access is still wide open until you physically turn the key.
That is a perfect analogy. Take the su program, which you use to switch users. When you run su, it starts with an EUID of root and a RUID of your current user.
Yeah.
It verifies the password, then it drops both the EUID and RUID to the target user's identity.
So where's the leak?
The leak happens if, before dropping privileges, the program opens a privileged resource, say a sensitive config file in etc. in write mode. If it opens that file but fails to close the file descriptor, that little number representing the connection the capability is leaked.
So when it drops privilege and runs the new shell.
That new lower privilege shell still has access to that open, writable file descriptor it inherited from its parent.
And we have a huge real-world example of this in our notes, the 2015 OS X Yosemite vulnerability.
Yes, that was a big one.
Yeah.
It was related to Apple's dynamic linker, dialed. Apple had introduced features that relied on environment variables like dial dprint a file.
Okay.
When dialed ran with root privileges for a SetUID program, it could open and write to almost any file path specified by that environment variable.
So the attacker could just set daily print a file to point at a super sensitive system file.
Precisely. Dialed would dutifully open the file with root permissions, but then, critically, it failed to close the file descriptor before dropping privileges and executing the main program. This leak allowed an attacker to write anything they wanted into files that should have been untouchable. Full privilege escalation.
It really shows how critical that cleanup after principle is.
It's everything.
Let's transition to the final major attack type tied to this. Command injection vulnerability. This isn't about where a program runs, but what it runs.
This is a classic, a consequence of mixing code and data.
Mm.
If a program takes untrusted input, maybe from an environment variable, and turns that data directly into a command that gets executed by a shell, you have an injection flaw.
It's a lot like SQL injection, but for the OS shell.
Very similar concept. Imagine a vulnerable program like the catal.cpp example in the notes. It's supposed to run a command based on a user-supplied file name.
Okay.
If the user inputs just a file name, file.txt, it's fine. But if an attacker provides a payload like file.txt, malicious command, the shell sees the semicolon and just executes the malicious command as a second separate instruction.
And what's the crucial detail our sources emphasize about the syntax for this?
The need for proper quotations. In a lot of vulnerable C programs, they pass the user input as a single argument. So if the payload is complex, you need to surround the whole thing with quotes. That ensures file.txt malicious command is passed as one single argument, which then forces the underlying shell to parse it and run both commands.
And once again, if that catal.cpp program has the SetUID bit set, the injected command runs with maximum privileges. This whole thing shows a terrifying pattern. The environment variables are just the delivery vehicle.
That's the perfect summary. They're the delivery vehicle for payloads that exploit weaknesses in these fundamental API calls. It all funnels back to a lack of control over the execution environment.
So what does this all mean for developers and security engineers? We've covered this multi-layered threat. How do we build systems robust enough to defend against these attacks?
Mitigation really rests on some fundamental secure coding principles. First and foremost, the principle of least privilege. A privileged program should only have the absolute minimum power it needs to do its job.
So using APIs like SetUID and SetUID to drop privileges as soon as possible.
As soon as they're no longer required. And you have to know the difference.
Can you quickly clarify that difference between SetUID and
Sure.
SetUID?
SetUID changes the real user ID and the effective user ID, the permanent drop in privilege for that process.
Yeah.
SetUID, on the other hand, changes only the EUID, which allows a program to temporarily drop privileges and then regain them later if it needs to.
Which is useful, but also requires more care.
A lot more care. And that ties directly into the principle of cleanup, after we discussed with capability leaks.
Absolutely non-negotiable.
Right. Before you drop any privileges, you must close or destroy all privileged resources. Every open file descriptor, every memory allocation. If you don't physically close that file handle, you're leaving the back door open no matter what user ID you switch to.
Beyond privilege control, it seems like we just need to stop using the most dangerous APIs, especially system.
Avoid this system. Call whenever humanly possible. Instead, developers should be using the exec family of functions. Execv is much lower level. It offers granular, explicit control.
How so?
When you use exec, you have to provide the full, non-ambiguous path to the executable. No more relying on the path variable.
And that directly addresses the path manipulation vulnerability.
It does. And what's more, execv requires you to explicitly pass an array of arguments and a controlled set of environment variables. By manually setting the environment, you prevent any external variable overriding. You ensure a clean slate.
But our sources had a warning about the exec family, too, that not all of them are safe.
That's right. You have to choose carefully. Functions like execlec, exevp, and exexvp, they still duplicate the shell's actions. They will perform path lookups. So if you use one of those, you've just reopened the door to the path vulnerability. You have to use execleave for secure execution.
And finally, data sanitation.
Always. Always sanitize untrusted data before using it, especially data from the environment. Use secure API functions like secure Tendia. In some systems, it returns the value only if the process is not running as SetUID, which is another great layer of defense.
We've successfully navigated from a simple configuration setting to complex layered system exploitation. I think the biggest takeaway here for you, the listener, is that secure programming is less about patching obvious bugs and more about constant vigilance over the implicit actions the operating system is performing on your behalf.
Precisely. We've shown how the dynamic linker and the system shell, both essential components designed for convenience, become these huge attack surfaces because they rely on dynamic environment variables. It creates this fundamental tension that can't really be resolved, only managed.
A final thought for our listeners to explore on their own.
To continue your research, I'd encourage you to look deeper into that tension. Research which modern OS components still run as SetUID, and what hidden environment variables, beyond the common ones we discussed, they might rely on to function. Understanding that hidden dependency map is really the next frontier of defense.
Absolutely fascinating. Thank you for providing the incredibly detailed source material that enabled this deep dive. Until next time.